C# and AI Masterclass by Edgar Milvis Volume 8, Chapter 8. Let's discuss Chapter 8, the Handlebars template engine for prompts. Moving on to theoretical foundations. The fundamental challenge in building sophisticated AI agents is not the model's intelligence, but the precision of the instruction delivery. As explored in Book 7, the architecture of large language model interactions, the transition from monolithic, static prompts to dynamic, context-aware systems is the hallmark of professional AI engineering. While simple string interpolation works for trivial cases, it collapses under the weight of complex business logic, variable data structures, and conditional reasoning required by modern agentic patterns. This is where the Handlebars templating engine becomes the backbone of prompt engineering within the Microsoft Semantic Kernel. Turning our attention to the cognitive load of prompt assembly. To understand the necessity of a templating engine like Handlebars, one must first visualize the architecture of a raw prompt versus a templated prompt. In a raw approach, an AI engineer is forced to perform string concatenation manually. This creates a high cognitive load and introduces fragility. Consider a scenario where an AI agent acts as a financial advisor. The prompt must change drastically depending on whether the user is a risk-averse retiree or an aggressive day trader. Without a template engine, the C# code would look like a tangled web of if-else blocks appending strings. We begin our prompt engineering journey by establishing the foundational role of our AI assistant. At line 1, we initialize a string variable prompt with the instruction, "You are a financial advisor." This is a critical first step in setting the AI's persona. By clearly defining its role up front, we guide the AI to adopt the appropriate tone, knowledge domain, and conversational style. Without this explicit instruction, the AI might respond in a generic or unhelpful manner, failing to leverage its specialized knowledge base effectively. This initial prompt acts as a high-level directive, ensuring all subsequent interactions are framed within the context of financial advice. At line 2, we encounter a conditional statement that checks the user profile. If the user profile is identified as retiree, we append specific instructions to our prompt. This is a prime example of dynamic prompt construction, where the AI's behavior is tailored based on user-specific attributes. For retirees, the advice typically shifts towards safety and capital preservation, as reflected in the appended string at line 3. This adjustment is crucial because a retiree's financial goals are fundamentally different from, say, a younger investor. Furthermore, at line 4, we introduce another layer of personalization. If the retiree has dependents, we add an instruction to ensure funds last for dependents. This demonstrates a granular level of customization, acknowledging that even within the retiree segment, individual needs vary significantly. This approach allows the AI to provide highly relevant and empathetic advice, avoiding generic responses that might not suit the user's life stage and responsibilities. Imagine if we didn't add this, the AI might suggest aggressive growth strategies, which would be completely inappropriate and potentially harmful for a retiree relying on their capital. Conversely, if the user profile is not retiree, as indicated by the else block at line 5, we steer the AI's focus towards high growth potential at line 6. This is a deliberate architectural choice to cater to a broader range of users, typically younger investors or those with a higher risk tolerance and longer investment horizon. By dynamically adjusting the prompt based on the user's profile, we ensure that the AI's recommendations align with typical financial objectives for different demographics. This prevents the AI from giving conservative advice to a young professional looking to maximize returns, or conversely, suggesting risky investments to someone nearing retirement. This conditional branching is fundamental to building a truly adaptive and user-centric AI application. It directly impacts the quality and relevance of the advice provided, making the AI feel more intelligent and understanding of individual circumstances. Finally, at line 8, we append the actual user query to our dynamically constructed prompt. This is the concluding step in preparing the AI's input. By including user query before the actual query, we explicitly signal to the AI that the following text is the user-specific question or request. This clear demarcation helps the AI differentiate between its internal instructions, the persona and focus settings, and the user's direct input. Without this, the AI might struggle to correctly parse the user's intent, potentially misinterpreting parts of the prompt as part of the query or vice versa. This structured approach to prompt concatenation is a best practice, ensuring that the AI can effectively understand both its role and the specific task it needs to perform for the user. This is architectural debt. It mixes logic, the if-else blocks, with presentation, the actual text. It is untestable, unscalable, and impossible for a non-developer to review. Moving on to the analogy, the master recipe book. The raw string approach, you scream instructions across the kitchen for every single order. Hey, for table 4, use chicken, but if they are allergic to nuts, use tofu, and if it's Tuesday, add the spicy sauce. This is chaotic. If the kitchen gets busy, you will make mistakes. The cooks get confused by the long, run-on sentences. 2. The handlebars approach. You have a standardized recipe card system. You fill out a card based on the order ticket. The card has placeholders, protein, a sauce, side dish. You don't write the full instruction every time. You just fill in the variables. Furthermore, the card has built-in logic, hashtag if is spicy, add jalapenos, /if. Handlebars is that recipe card system. It separates the structure of the prompt, the template, from the data, the variables. It allows the AI engineer to design the recipe once and simply inject ingredients, data, to generate the final instruction. Turning our attention to the mechanics of Handlebars in C#. Handlebars is a logicless templating engine, but logicless is a misnomer. It means it lacks traditional imperative programming flow, like for loops or switch statements. Instead, it uses expressions and helpers to control the flow of data rendering. In the context of the semantic kernel, we utilize the handlebars.net library. When we define a prompt template using handlebars, we are essentially creating a function that takes a JSON object, the context, and returns a string, the fully formed prompt. Let's discuss 1. Variable substitution, the. Why this matters for AI. It ensures that the AI receives specific, accurate data. If we are building a code review agent, we cannot simply say, review this code. We must say, review this C# code snippet, which was written by author, and relates to module name. Moving on to 2. Contextual awareness. The semantic kernel passes a kernel arguments object, essentially a dictionary of key-value pairs, to the template engine. Handlebars traverses this object graph. If your data structure is nested, this JSON snippet represents a common data structure for user information. Notice how it's organized hierarchically. The outermost key, user, acts as a container for all user-related data. Inside user, we have another object, profile, which groups specific attributes about the user's profile. This nested structure is a best practice for organizing complex data, making it more readable and maintainable. Imagine if all these keys were at the top level, it would be much harder to discern which attributes belong to the user versus other entities. This hierarchical approach also helps in preventing naming collisions if you were to combine this data with other JSON objects that might also have a name or tier field. The template hello, user.profile.name, your tier is user.profile.tier, resolves this automatically. This allows for deeply complex context injection without manual flattening of data. Now, let's talk about 3. Iteration, the #each helper. This is where the engine transforms from a simple formatter to a dynamic generator. In AI applications, we often need to provide the LLM with a list of examples or context. Imagine we are building a sentiment analysis agent. We want to provide few-shot examples to the model, referencing the concept of few-shot learning from Book 3. We have a list of previous inputs and outputs. Without a loop, we would have to manually concatenate strings. Example 1, input, bad service, output, negative. Example 2, input, great food, output, positive. With #each, the template becomes. This block of text represents a prompt template, which is a crucial component in large language model, LLM, applications. Think of it as a meticulously crafted instruction set for an AI. The first line, analyze the sentiment of the following user feedback, clearly defines the primary task for the LLM. This is a directive that guides the AI's understanding and response generation. Without such a clear instruction, the LLM might interpret the subsequent text in many different ways, leading to inconsistent or irrelevant outputs. We are essentially providing the AI with its mission statement for this particular interaction. The #each block iterates over the examples array. It is robust. If the array is empty, the block simply renders nothing, preventing syntax errors in the final prompt. Now, let's explore 4. Conditional logic, the #if # unless helpers. This is the engine of context awareness. AI agents often operate in modes. A customer service agent might have access to a user's purchase history, but only if the user is logged in. Using handlebars, we can dynamically alter the system's persona and instructions. This line, "You are a helpful assistant," serves as a foundational prompt or an initial instruction for the AI model. In many AI systems, especially those built on large language models, the very first input often sets the persona or the general behavior guidelines for the AI. Think of it as telling a new employee their job title and primary role. This isn't just a casual statement, it subtly influences the AI's tone, helpfulness, and overall approach to subsequent interactions. Without this, the AI might default to a more neutral or even unhelpful stance, depending on its pre-training. It's a critical, albeit simple, instruction for guiding the AI's fundamental interaction pattern. Here at line 2, we encounter #if user.is authenticated. This is a conditional statement, common in templating languages like Handlebars, which Semantic Kernel often leverages for prompt engineering. This if block checks a specific property, user.is authenticated. This property is expected to be a Boolean value, indicating whether the current user interacting with the AI has been successfully authenticated. This is a fundamental security and personalization check. If user.is authenticated evaluates to true, the statements within this block will be processed, otherwise, they will be skipped, and the else a block, if present, will be considered. This architectural choice allows for dynamic prompt generation based on the user's login status, which is crucial for tailoring responses and accessing sensitive information. Notice how at lines 3 and 4, you have access to the user's order history, and current order count, user.orderCount. These lines are executed only if the user is authenticated. This demonstrates a core principle of personalized AI experiences, only reveal or access user-specific data when authorized. The first line informs the AI itself, and implicitly, the user, that it can now leverage more contextual information. The second line, user.orderCount, is a placeholder that will be dynamically replaced with the actual order count from the user object. This is a powerful way to inject real-time, user-specific data directly into the AI's prompt, allowing it to generate highly relevant and data-driven responses. Without this conditional access, an unauthenticated user might inadvertently get information they shouldn't, or the AI might attempt to access non-existent data, leading to errors or security vulnerabilities. At lines 5 through 7, we see a nested conditional, #if user.orderCount5. /if. This is a further refinement within the authenticated user block. It checks if the authenticated user's order count is greater than 5. This is a common pattern for segmenting users into different tiers or groups based on their activity or status. If user.orderCount exceeds 5, the AI is instructed, the user is a VIP. Be extra polite and offer expedited shipping. This isn't just a polite suggestion, it's a direct instruction to the AI to modify its behavior and potentially its output based on a specific user attribute. This kind of dynamic rule-based prompting is essential for building sophisticated AI agents that can adapt their responses, offers, and tone to different customer segments. Imagine a customer service bot. Treating a high-value customer differently can significantly impact customer satisfaction and loyalty. This architectural decision directly supports such nuanced interactions. Here at lines 8 through 10, we have the else block, followed by the user is anonymous. Do not ask for personal data. This else block is executed if the initial #if user.is authenticated, a condition at line 2 evaluates to false, meaning the user is not logged in. This section is crucial for handling anonymous users gracefully and securely. The instruction "do not ask for personal data" is a critical guideline for the AI, ensuring compliance with privacy best practices and regulations like GDPR or CCPA. Without this explicit instruction, an AI might, by default, try to gather more information, which would be inappropriate and potentially illegal for an unauthenticated user. This demonstrates how prompt engineering isn't just about making the AI helpful, but also about making it compliant, ethical, and secure by defining clear boundaries for its behavior based on user context. It prevents the AI from overstepping its bounds when user identity is unknown. This is the master recipe book in action. The structure of the prompt remains constant, but the content morphs based on the user object. This reduces the token count, saving money, and reduces confusion, improving accuracy, by hiding irrelevant instructions. Turning our attention to architectural implications, the template store. One of the core tenets of the core of AI engineering is separation of concerns. In a robust system, the C# code should not contain the prompt text. The prompt text is a content asset, not code. Using Handlebars allows us to store templates as physical files, .hbs files, in our file system or a database. The C# code simply loads the file and executes it. Here, we're seeing a common pattern in AI engineering for defining prompts, externalizing them from the code. Notice at line 2, we read the prompt template from a file named codereviewer.hbs. This HBS extension suggests we're using Handlebars, a popular templating engine. This architectural choice is crucial for maintainability and flexibility. Imagine if your prompts were hard-coded strings within your C# files, any change to the prompt would require recompiling and redeploying your application. By externalizing it, prompt engineers or even non-developers can iterate on prompt design without touching the core application code. This separation of concern significantly accelerates the prompt engineering lifecycle and allows for A/B testing of different prompt versions without code changes. The template content variable then holds the raw, uncompiled template. Versioning: you can git-diff a.hbs file much easier than a string inside a C# file. 2. A/B testing: you can load template_A or template_B dynamically to test which prompt yields better results from the LLM. 3. Localization: you can have prompt_n.hbs and prompt_fr.hbs, swapping them out based on the user's locale without changing a single line of application logic. Now, let's talk about integration with agentic patterns. In the context of agentic patterns, Book 8, Handlebars acts as the plan component of the React reason plus act loop. The problem: the LLM returns raw data, JSON. The agent needs to summarize this for the user. The summary style depends on the user's request. Give me the temp versus write a poem about the weather. The solution: the agent selects a Handlebars template based on the user's intent. It feeds the raw JSON into the template. The template applies the requested style, poetic, concise, technical, and generates the final output. A diagram illustrates how raw JSON data flows from a C# application into a Handlebars template engine, which applies a specific style, such as poetic, concise, or technical, before passing the formatted prompt to a large language model, LLM, for final output generation. Let's discuss theoretical foundations. The Handlebars template engine is not merely a syntax convenience, it is a structural necessity for scaling AI applications. It enforces consistency: every prompt generated follows the defined structure. 2. It manages complexity: it allows developers to handle complex, nested data structures and conditional logic without polluting the application code. 3. It enables modularity: by treating prompts as templates, we can reuse, version, and swap instructions easily. Without this tool, building an agent that can handle multiple users, multiple tasks, and dynamic context would result in unmaintainable, spaghetti code, rendering the agent brittle and impossible to iterate upon. Handlebars provides the robust scaffolding required to turn a simple LLM call into a production-grade AI system. Let's discuss basic code example. Here is a simple, Hello World level code example demonstrating the Handlebars template engine within the Microsoft Semantic Kernel. Turning our attention to real-world context. Imagine you are building a customer support chatbot for an e-commerce platform. When a user asks about their order status, you cannot simply ask the AI to check the order. You must provide structured data, order ID, current status, shipping carrier, and a specific format for the response. Hard-coding strings is messy and unscalable. Handlebars templates allow you to separate the logic of the prompt, the structure, from the data, the specific order details, enabling you to reuse the same prompt template for thousands of different orders. Now, let's talk about code example. Here at the beginning, we import essential namespaces. Notice how Microsoft.Semantic Kernel is brought in. This is the core library that provides the framework for building AI applications with Semantic Kernel. We also include Microsoft.Semantic Kernel, connectors.openai, which would be crucial if we were directly interacting with OpenAI models. System.component model is used for attributes like description and kernel function, which help define and document our plugin functions. System, text, JSON is vital for handling JSON serialization and deserialization, allowing us to work with structured data. Finally, system, threading, tasks is included for asynchronous operations, a common pattern in modern C# applications, and system, console for basic output. Look at line 8, where we define our order status plugin class. This class is designed to encapsulate a specific piece of business logic, in this case, retrieving order details. The kernel function, get_order_details, attribute on line 12 is critical. It registers this C# method as a callable function within the semantic kernel. This means that an AI model, through a concept called function calling or tool use, could potentially invoke get_order_details when it determines it needs real-time information to fulfill a user's request. The description, attribute on line 13 and 14 provides human-readable explanations that help the AI model understand what the function does and what its parameters mean, which is crucial for effective function calling. We pass in the order ID as a string parameter, which is how the AI would specify which order it's interested in. Observe lines 16 through 28. This section simulates fetching data. In a real-world application, getOrderDetails would typically make a call to a database, an external API, or a microservice to retrieve the actual order status. However, for this example, we're returning a hard-coded JSON string representing mock order data. This approach simplifies the demonstration, allowing us to focus on how Semantic Kernel integrates plugins and templates, without needing a complex backend setup. The JSON serializer, serialize call on line 27 converts our anonymous object into a JSON string. This choice to return JSON is deliberate. It's a common format for data exchange and allows for flexible parsing and display by the calling application or the template engine, as we'll see later. Moving to line 31, we have our program class and the main method, the entry point of our application. Notice the async task main signature. This indicates that our main execution flow can handle asynchronous operations, which are common when dealing with I/O-bound tasks like API calls or database queries, even if this specific example doesn't directly perform them. At line 39, we initialize the semantic kernel using kernel.createBuilder. This builder pattern is a best practice for constructing complex objects like the kernel, allowing for clear, step-by-step configuration. Crucially, on line 42, we register our order status plugin with the kernel using builder plugins.addFromTyped order status plugin. This step makes the get_order_details function available to the kernel, meaning it can be invoked either directly or indirectly via prompt templates or AI orchestration. Now, let's examine the handlebars template string defined from lines 47 to 61. This is a handlebars template, a powerful templating language that allows us to combine static text with dynamic data. Notice the syntax. These are placeholders for variables that will be injected into the template at runtime. For example, order ID and order_details.order_ID will be replaced with actual values. The structure of this template is designed to create a helpful and informative response for a customer support assistant. The use of handlebars here is a deliberate choice for its readability and flexibility compared to simpler string interpolation, especially when dealing with more complex data structures or conditional logic, which handlebars supports through constructs like #with and #each, though not fully utilized in this simple example. At line 63, we create a prompt template config object. This configuration is essential because it tells Semantic Kernel how to interpret and render our handlebars template. The most important part here is template format equals handlebars on line 67. Without this explicit setting, the kernel would default to its internal templating language, SKL, and our handlebars syntax would not be correctly processed. This highlights the flexibility of Semantic Kernel to support different templating engines. Then, on line 70, kernel.create function from prompt config, takes our configured template and turns it into a callable kernel function. This means we can invoke this template just like any other function registered with the kernel, passing it arguments and receiving a rendered string back. This abstraction simplifies the process of generating dynamic prompts. Lines 73 through 80 demonstrate how we prepare the input data for our handlebars template. First, we create an instance of our order status plugin on line 75. While the plugin is registered with the kernel, we're invoking its getOrderDetails method directly here for demonstration purposes, simulating a direct data retrieval. The raw JSON string on line 76 contains the serialized order details. Crucially, on line 79, we deserialize this raw JSON into a JSON element. We use JSON element instead of a strongly typed class because it provides a flexible, schema-agnostic way to represent JSON data. This allows handlebars to access properties like order_details.order_ID dynamically without needing a predefined C# class that matches the JSON structure, making our template more robust to potential changes in the data schema. This is a powerful pattern for handling dynamic or evolving data. Observe lines 82 through 88, where we invoke our prompt function. Await kernel.invokeAsync, prompt function, new kernel arguments. Is the method call that triggers the template rendering. The kernel arguments object is where we pass the data that the handlebars template expects. Notice that the keys in kernel arguments, order ID and order details, directly correspond to the variable names used in our handlebars template, e.g., order ID and order_details.order_ID. This mapping is fundamental to how the template engine populates the placeholders. By passing order data, our JSON element, as order details, handlebars can then navigate its properties using dot notation, such as order_details.order_ID, as defined in our template. This is how the dynamic data is merged into the static template structure. Finally, at lines 90 through 93, we output the result of our template rendering. Right line, rendered prompt, provides a clear separator in the console output. Right line, result.toString, then prints the fully rendered string. This result.toString is the final prompt that, in a real application, would be sent to an underlying large language model, LLM. This step is critical because it demonstrates the ultimate goal of prompt templating, to construct a well-formatted, context-rich input for the AI. By observing this output, we can verify that our plugin successfully fetched the data, and our handlebars template correctly integrated that data into the desired message format, preparing it for an LLM to process. The diagram illustrates the final stage of a data pipeline where a fully rendered string is generated and prepared for submission to a large language model, LLM, such as GPT-4. Now let's talk about common pitfalls. Mismatched template format, mistake, forgetting to set template format equals handlebars in the prompt template config. Result, the kernel defaults to the standard template format, often liquid or simple string substitution. If your template uses #if or #each handlebars syntax, the kernel will throw a parsing exception or render the raw tags as text. Fix, always explicitly define the template format. 2. Null reference in object paths, mistake, passing a null object or a property that doesn't exist when using dot notation, e.g., order_details.tracking_number, where order details is null. Result, handlebars typically renders an empty string for null values, but if you try to access a property on a null object during a helper execution, it may throw a runtime exception. Fix, use handlebars conditionals, #if order details, /if, to guard against nulls. 3. Data type confusion, mistake, passing a JSON string directly as a value instead of deserializing it. Result, if you pass the raw JSON string, ID1, as order details, handlebars will treat it as a string literal. Accessing order_details.id will fail because order details is a string, not an object. Fix, ensure complex data is deserialized to a dictionary or object structure before passing it to kernel arguments. 4. Escaping braces, mistake, trying to include literal or in the output text without escaping. Result, handlebars attempts to interpret them as tags, leading to rendering errors. Fix, use the triple-stack variable if you want to output raw HTML/JSON without escaping, or use the specific handlebars escaping mechanism if you want to render the literal characters. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. Thank you for your attention. This lesson is excerpted from Volume 8, Chapter 8 of the C# and AI Masterclass ebook series and from the volume, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns. You can find all the details here, https://github.com/edgarmilvus/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.